All right, 4A. We're going to talk about taking the derivative of functions that are in exponential form. So these are exponential derivatives. What I don't want to happen is for you to confuse the exponential rule with the power rule. So we've got the power rule from before. And the power rule applies when the power is a constant. Now, that can be as simple as a square or a cube. It can apply to square roots because those powers are constant. It can apply to even weird things like this. An example, y equals sine pi of x. Like, that would be power rule because the power is pi and pi is a constant. So you'd think of it as sine of x to the pi, and then when it's time to take the derivative, you would apply the product rule the same way that you would have done it if it was a square. If it was a square, you would have pulled the power to the front, and in this case you'd pull the pi to the front and you'd have sine of x to the, and what's the rule? What do you do to the power after you've brought it to the front? Decrease it by 1, so then it'll be pi minus 1. And it looks awkward and we don't like it, but that's the appropriate way to do it because the power is a constant. And then we do remember that this does require the chain rule, so we would additionally have cosine on there. Right, that's the power rule. There is a separate exponential rule which applies when the power is what? What's the difference? When the power is not constant, and if you're not constant, then you are a variable. So that is the exponential rule. And so it is important you do not confuse those two, that this will apply when the power is not constant. In other words, it is a variable. And here's how that rule goes. So if you have a function, and we'll call that a to the u. So u is a variable now, it's changing. It is not a constant value. Then how do you take, but a is a constant value. Okay, that base is representing a constant number. So a is constant, u is not constant. Then the derivative looks like this, f prime. It's the same function, a to the u, times a couple different chain things. So it's a to the u times the natural log of a, and then also times the prime of u, or u prime. So the derivative, so it's like two pieces of a chain rule that they each require. One is the natural log of the part that is constant, and then the derivative of the part that is not constant. All right, so again, you end up with this part being constant, and that part there being not constant. And that's the rule. That's all it is. Now we're going to apply it, and the functions get complex. The complexity is not in the rule. The rule is very simple. The complexity comes when you have very complex functions that you're applying the rule to. All right, so this is worthy of being in a box because it is important. We only have one rule to go. The only other rule that you need to learn is the logarithm rule, and you'll learn that tomorrow. And then you have learned every rule that applies to every derivative. And so you should be able to apply those to take very complex derivatives. All right, let's practice. So I'm just going to give you a series of functions that are exponential in nature, so their powers are not constant, and then we'll work on practicing taking the derivative. They're going to get increasingly more complex as we go. So let's start with a fairly simple equation or function that would be 3 to the power of x squared. So 3 to the power of x squared. We've got the 3 is the constant part and the power is not constant. So the rule for the derivative would be the exponential rule, and what would apply would be the function itself, 3 to the x squared, times the logarithm of the constant part, so ln 3, times the derivative of the non-constant part, which would be 2x. And that can't be simplified. There's nothing to combine. It's just a product, and that's the final answer. I suppose if you wanted to write it in a different order, you'd maybe start with 2x, and then you'd have ln 3, and then maybe you'd end with 3 to the x squared, but the order of multiplication is irrelevant, so you're not going to lose points one way or the other depending on what order you put the multiplication in. Okay, that was a pretty straightforward one. Any questions on that? Okay, let's try another. Oops. Okay, how about a function that's defined as 5 to the cotangent of 3x. So we recognize that the constant is the number 5, and the part that's varying, or the variable, is the cotangent of 3x. So when we take our derivative, g prime, we'll have the function itself, so 5 to the cotangent of 3x, times the logarithm of the constant part, that's ln 5, and then the derivative of the non-constant part. So let's remember, what is our derivative of cotangent? Negative cosecant squared of 3x, but right, times the additional chain rule of 3, because I had to say the cotangent of 3x, and so then I have to take the derivative of the cotangent part, and I have to take the derivative of the number 3. So if we were going to clean this up a little bit, I think maybe I would put the negative 3 in the front, followed by the ln 5. So those are all constant pieces, the negative, the 3, the ln 5. Then maybe put cosecant squared of 3x next, and then maybe at the very end put my 5, the original function. But again, the order of multiplication is irrelevant. Any questions so far? All right, let's try another one. How about p of x being defined as the function e to the sine of the square root of x? Again, this would fall under the exponential rule because e is a constant and the power is not. So my p prime, well, how about somebody else? Somebody else want to try it? All right, Joanne.
Okay, so the original one is the logarithm of sine, right?
Well, first I got to do the original one. Okay, that always comes first. So e to the sine of rad x. All right, times.
And then logarithm of e.
Okay. And times?
Times cosine of x, rad x, times 2x times dx.
Not 2x. This isn't x squared. This is the square root of x. So I got to think about how to take that. It's 1/2 x dx, not 2x dx.
Oh, yeah, I meant 2.
Okay. All right. So then we could,
Yeah.
to the, okay, very good. Yep, we need to add the negative 1/2 as our power. All right, so when we clean all this up, wow, that got really tiny. When we clean this up, we want to look for maybe what we would put first. And of all, well, first of all, what do you notice about the natural log of e? That's 1, okay? So it's not like it cancels, but it's the value of 1, so we can replace that. I think what I'd probably put first is cos rad x, and then maybe the e to the sine rad x part, because that was what I was taking the derivative of. And then over the 2, which came from the half, and the square root of x. And that doesn't simplify any further. That would be all I would have.